Okay, so remembering that we are using conservation momentum, but momentum is a vector, meaning we write our equation like this for momentum, so the direction comes from the velocity. We're still using conservation of momentum, but now we want to apply this as a vector, which basically just means we have to pick an x and y direction and break everything up into perpendicular components. Conveniently, if we draw this scenario out, okay, we're using these two cars. One is a toy car heading north, that's a Cadillac at a speed of 3 meters per second, and it collides with a small Volkswagen that's heading east. So if we draw this out, here's our before picture. Here, I'm just going to draw these as rectangles. Here are our cars. We could put some little wheels on them if we want. So this is a terrible drawing of a car. I apologize. But here are our cars, okay? And they have velocities, initial velocities. We'll call this V naught, and we'll call this V Cadillac, okay? Now these cars have masses, so the mass of, so this is our Volkswagen, and this is our Cadillac. The mass of our Volkswagen we'll call little m, that's 2 kilograms. And then the mass of the Cadillac we'll call big M, and that's 3 kilograms, okay? After the collision, the skid mark tells us the direction. So we have these two cars, they're stuck together, but because we know they have a skid mark, they have some final velocity that's at 35 degrees from our x value, okay? So we still need to figure out our final velocity in x and y components, but now our mass should be m plus m, which is our total mass, which is 5 kilograms. And we want to break up our velocity into v final cosine 35 and v final sine 35. So now we have x and y components. So when we write this out, when we're using our conservation and momentum, that means our initial momentums should be in the x direction. So that would be mass, which is the small mass for VW, times v naught. And our momentum in the y direction is going to be big M VC. Now when we get to the later part, our final velocity in the x direction should be m plus m v final cosine theta, and our final velocity in the y direction is m plus m v final sine theta, where theta is 35 degrees. So now, if we want to figure out our change in momentum is 0, that's the same as saying momentum initial equals momentum final, but these are vectors. So we do this for the x. So in the x direction, we have m v naught is equal to m plus m v final cosine theta. And then in the y direction, we have big M, V Cadillac is equal to m plus m v final cosine theta. Now, if you look at the things we know and don't know, we're looking for this ultimately, because we want to know how fast the toy VW was going before the collision. But there's another thing we don't have, which is v final. However, if we know our system of equations, we have 2 equations and 2 unknowns, so we should be able to solve. We'll first take this equation and we'll solve it for v final. So our v final, doing some algebra, should be big mass times the initial velocity of the Cadillac times divided by the total mass. Oops, sorry, this should be sine. Sine of theta. We plug in our numbers. This should give us 3 kilograms times 3 meters per second divided by 5 kilograms sine of 35 degrees. When you plug all that in, you get 3.14 meters per second. So that is this final speed. Okay, about pi meters per second. All right, so that's our intermediary value. This is our V final, and we still need to find V initial. So we go back to this equation and we solve for V naught, which gives us m plus m V final, which is what we just solved for, cosine 35 degrees divided by small m. So this gives us 5 kilograms, 3.14 meters per second, cosine 35 divided by 2 kilograms. And when you plug all that in, you get this value of 6.43 meters per second. And that is our, V final. Sorry, V initial. So that is the initial speed, initial speed of our Volkswagen.